Okay, welcome back, everybody. Um, last time ended with discussion of Kruskal's algorithm for finding minimum weight spanning tree, and in your homework, you're gonna deal with at least one more algorithm for doing the same. Um, that leads nicely into next natural question, which is, of course, how do I? We touched on this a little bit last time, where I asked whether or not um, a given spanning tree was unique in some sense, and we saw that even a minimum weight spanning tree may not be unique in a graph. In fact, you have a homework problem from this upcoming homework that's due Friday that also asks, what does it mean if you have a graph that has a single unique spanning tree? What does that mean about it? It turns out it's pretty special. There's only there's only one way that can happen. That's if the graph is a tree itself. So in general, natural question of how many spanning trees exist on some number of vertices. So that is directly the thing that we're going to be asking now today, and this is one of the first instances of the combinatorics really kicking in. Of course, we're going to see a number of, no pun intended, going to see a number of these things in the next chapter when we get to combinatorics, of course, looking in the other direction, but here going from our graph theory concerns immediately into combinatorial types of arguments is this is like, even though we've seen it a little bit previously, this is kind of the first place it's really kicking in. So first question, how do I count number of, we'll say, different labeled trees on, say, n vertices? Let's just try kind of the naive thing, right? Let's do a quick example and say, okay, what if I label these vertices? We'll say this is A, this is B, this is C. I want to count a spanning tree here. So when of course, it being a tree, it needs to be connected. So if it's a tree on n vertices, then it is a spanning tree for a graph containing these n vertices, right? That's how we're relating this to the question of counting spanning trees, because given a graph G on n vertices, of course that graph could look like whatever, right? There could be however many edges here. Um, Counting the spanning trees, though, is counting the distinct number of trees on these labeled vertices. And so what do I have? Well, basically, you might think an easy way to count these is to basically consider, we know we can't make a cycle. It wouldn't be a tree then. So then it's really a question of which vertex has degree 2, right? Which vertex has degree 2 and which vertices have degree 1? That's really the question here. So maybe you say, okay, A is going to have degree 2, so the first tree I draw is here. Okay. I'm going to draw the same vertices A, B, and C. And of course, B could have degree 2, which would lead to a tree that looks like that. That, of course, is a distinct tree from this because the corresponding vertices are different here. Here, A has degree 1. Here, it has degree 2. And similarly, maybe my last example. So here's A, B, C. C is going to have degree 2. So there it is. Okay. Are there any others? Well, no. Right. This is all of them on 3 vertices. There's not a whole lot. What about 4 vertices? So let's label my vertices A, B, C, D. Might as well. So we'll say A, B, C, D. Now you can try to do what you did before about which vertices are going to have degrees 1 and which are going to have degrees 2 or more. But this is a little trickier here because I have 4 vertices, so there's some more options here, right? I could have a path, right? This could be the path P4. That's an option. In fact, thinking of a path as kind of the most basic form of tree is not that's not a bad way of thinking about it, right? When we were trying to enumerate the different types of unlabeled trees before, that the path for every number of vertices, the path on n vertices was kind of our base example of a tree. Um, okay, so here's one way. Let's do this. Well, unlike before, right, I could have something here like this. That's a tree. But I could kind of do this for every vertex. And you might complain here and say, well, you're not being really very systematic here, right? I don't see the pattern between these two. And it's true. Once I see this, maybe I'm going about listing these and I say, oh, I could do this, except I could alternate the vertices on which this happens. So C could be the thing with degree 3 and all the others are leaves. A could have degree 3, the rest are leaves. B could have degree 3, the rest are leaves. So I could do that. And you quickly see that, like, I'm going to get 4 like this. I'm going to get 4 like this. And I'm basically going to get 4 types that are, in a way, permuted around the vertices here 4 times. And so this is going to lead to 16 total configurations. But if I show you what these are, rather than us actually listing them, here we go. So these are all of the options. Notice it is like you took this shape and just said, well, say now what we're really doing is saying which edge is missing from the cycle here. So here the edge missing from the cycle is AC, here it's AB, here it's BD, and here it's CD. And that is one way of thinking about these. This last row was the 4 I suggested from our example, where A has degree 3, the rest are leaves, B has degree 3, the rest are leaves, D has degree 3 here, the rest are leaves, and C has degree 3 here, the rest are leaves. Now we have this ZN sort of pattern, and here they're reflected, right? So there's that symmetry, but all these are different. And then there's this configuration here, right? The fish configuration, or it looks like, I can't remember what that rune is called, but it looks like some Nordic rune. This row here is another example of how we have this symmetry, right? Because we have 4 vertices here, that's how it works in this way. And so that is for 4. The number of labeled trees on 4 vertices, there are 16 of them. These are the only ones. So very carefully, you can think about what you're doing in each case in terms of the degrees and convince yourself that you've exhausted all possibilities. Now, I could then ask you, well, what about on 5 vertices? Right? So on 5 vertices, how would you do this? And you might set about doing it, right? Of course, you can theoretically do it by brute force. But you might want to take a look at the at the result first to tell you what number of these you can expect before you set about doing it. Um, so here's just for you. Draw a few on 5 vertices. Just to see. Now, this is answered by the following. So our answer, well, the question was, how do I count? This answer isn't going to tell you how, although the proof of it will tell you how. The answer is just telling you what the number is. So maybe I should say it's really telling you what the number is. It's not telling you how to count, although, as I said, the proof of this is going to tell you how to count these. So this is called Cayley's tree formula. So, so what does Cayley's tree formula say? There are n to the n minus 2 distinct labeled trees of order n. So, if I look at this and I believe that this result is true, on 5 vertices, how many distinct labeled trees of order 5 there are going to be? So 5 to the 5 minus 2, so this is 5 cubed, or 125 such trees. So that's why I said might want to look and see whether or not you feel like brute forcing 125 cases here and making sure that you've counted them all nicely. So the question is why? Where does this come from? Why that number? N to the n minus 2. What is the idea here? So proof of Cayley's tree formula. What is the idea? The idea, this was due to Proofer. And this method is, I'm actually going to go through the algorithm in both directions to show, this is essentially proof by an algorithm that sets up a one-to-one correspondence with a set having a size that I can very easily determine. And so what is the idea here? The idea is to put these trees, so put the number of distinct labeled trees on n vertices in one-to-one correspondence with a set with determinable size. Specifically, this is the set of all sequences of length n minus 2, so sequences involving n minus 2 terms whose entries come from the set on those labeled vertices. Now, obviously, you don't have to use numbers to label them, right? It doesn't matter. The point is that the size of the set, the cardinality of this set that they come from is n. In this case, so the number of such sequences, well, this is our, This is like your counting 101, right? The multiplication rule. I'm choosing n minus 2. There are n minus 2 entries in the sequence. They can be any entry in the set. There's n options for each one. So there's n times n times n times n minus 2 copies of that. So n to the n minus 2 is the number of such sequences. And so you say, distinct labeled trees on n vertices, that is in one-to-one correspondence with sequences of length n minus 1 whose entries come from this set. And this set has size n to the n minus 2. Okay, so that's the idea for the proof. Then all I need to do is basically describe this correspondence, and I'm essentially done with the proof. Okay, so to see the one-to-one correspondence, we'll look at it in both directions. I'll put in both directions in quotes, because what does this mean? So both directions here refers to assigning a sequence to a labeled tree and assigning a labeled tree to a sequence. So these are the two directions. So first thing, assigning a sequence to a labeled tree. So I'm going to list these in steps. So what am I given, first of all, before I start numbering these steps? So I'm given a tree with vertices labeled 1 to n. And we'll call it T, with vertices labeled 1 to n. Okay, so it's a tree on n vertices. First step, let I equals 0, let t sub 0 be equal to t. So our initial tree is just the tree we start with. Okay. Second step, find the leaf on t sub I with the smallest label and call it v. Okay, so smallest label here implies one that the index set has an ordering on it, that we know what smallest is. So this is why typically we're going to use numbers here for the index set. If you have an ordering right on your set, then you can do it relative to that ordering. Doesn't matter, but yes, this implies there's an ordering here. So when we say smallest label, we mean the smallest index used to describe this thing, calling that v. I haven't described how to come up with a sequence yet, right? Right now I'm just identifying parts of the tree. Okay, now I record in the sequence the label of V's neighbor. V is only going to have a single neighbor because it's a leaf, so it has degree 1, right? So record in the sequence the label of V's only neighbor. So I'm just stressing that at this step you should not have a choice. That gets recorded in the sequence. To iterate to get to the next tree that I'm going to do this process on, I remove V from T sub I to create a new tree. Remember, at the 0th step, we are at T, so this is basically finding leaf with smallest label, calling it V, looking at its neighbor, putting that as the first term in the sequence, removing V, which leaves me with a tree on n minus 1 vertices, right? And now I'm going to do the same thing. I'm going to iterate this process. So anyway, remove V from T sub I to create a new tree, T sub I plus 1. This is how we get our next tree in the process. If it's possible that this was it, right? At this point, my next tree is like K2, right? So if T sub I plus 1 equals complete graph on 2 vertices, right? Just 2 degree 1 vertices, then stop. Otherwise, increment I by 1 and go back to step 2. I labeled it with Roman numerals, so. Okay. And so, this is how this process goes. Let's see how this works. So I am going to, let me give an example. So the tree in question, which I'll call T naught, our initial step in this process, is the following. How do I want to label this? So this is 2, this is 4, this is 3, this is 6, this is 1, this is 5, and this is 7. And how do I want to draw the tree in? There. Okay. Now, I have let my tree T be this T naught. I'm looking for the leaf on T naught with the smallest label. So I'm looking for the leaf with the smallest label, and here's a leaf, here's a leaf, here's a leaf, here's a leaf. The one with the smallest label's here, it's 2. Okay, so I've identified that. What do I do with it? I record in the sequence the label of V's only neighbor. So the only neighbor that this lowest numbered leaf has is 4. So maybe I'll put a column over here of the sequence that I have at each step. And so 4 gets recorded. I need to remove V from T naught to create a new tree. If what I've ended up with after that is K2, I stop. Otherwise, I increment I by 1 and I go back and try to do this whole process again. So now I'm removing this vertex to have T sub 1. So what does T sub 1 look like here? T sub 1 is that tree except with vertex label 2 removed. So I have 4, 3, 1, 5, 7. So now I'm doing the same thing. I'm finding the leaf on this new tree T sub 1 with the smallest label. So where are the leaves? Here, 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 and here. The one with smallest label, so 4, 5, 6, and 7 are the leaves. The one with the smallest label is 4. Its only neighbor is 3. So at this step, my sequence becomes 4 and then 3. and then I remove this vertex to iterate and go to my next tree, T2, which looks like this. Okay. Next, do the same thing. The leaves now are 5, 6, and 7, right, are the only leaves. The smallest labeled one is 5. Its only neighbor is 1, so that gets recorded. Vertex 5 gets removed. Now I only have 2 leaves, 6 and 7. The smallest labeled one is 6. Its only neighbor is 3, so the sequence becomes 4, 3, 1, 3. Vertex 6 gets removed. So now the tree that I have here is this T sub 4, just 3 vertices. There's only 2 leaves, 3 and 7. The smallest numbered one is 3. Its only neighbor is 1. Therefore, the sequence becomes 4, 3, 1, 3, 1. Removing vertex 3, I end up with the complete graph on 2 vertices. So I stop and say that this is the sequence consisting of 5 entries here. Of course, each of these, so here's my sequence consisting of 5 terms describing this process of assigning this sequence with 5 terms to this graph. Okay. So this, to this tree. This tree, of course, is a tree on 7 vertices. So the total number of labeled trees on 7 vertices, according to Cayley's tree formula, is going to be, this is going to be 7 to the 5. So there are 5 slots. Any of these slots could be 1 through 7, right? Now, the only way that that count matches up, of course, is if we can go in both directions. So I said we're going to talk about this in both directions. Here is the direction of assigning a sequence to a labeled tree. This is called a proofer sequence. If you like. So this is a proofer sequence for such a tree. But here's the thing, right? All this says, even if we convince ourselves this is, this is a well-defined, not ambiguous thing, we can always do this. This says that for a labeled tree, we can assign it a sequence, and it seems like this sequence has the right count. But in order to make sure this doesn't just sit inside that set of sequences, we need to make sure that we can recover exactly this tree from a given sequence, right? So that if I start with one of these sequences, the tree that I get out of it is not ill-defined. It's not ambiguous, right? If there's some choice there, if it's ambiguous, then that might suggest that the count is off, right? So the importance here of the one-to-one correspondence is that this is one-to-one correspondence in the sense that is very much one-to-one and on-to in the sense of functions, so that you have this well-defined inverse, that there's no ambiguity going back and forth between these things. So the question, how do I go in the other direction? All right. So here is one question. First of all, and you're gonna investigate this. Notice In the original tree, do any of the leaves show up? Well, what are the leaves of the original tree? The leaves are vertex 2, 6, 5, 7. And none of those show up in this sequence. And the question is that a coincidence? Well, no. It turns out each vertex of T, we'll say the vertex V of T, shows up in the sequence well, let's see if we can notice a pattern before I write it down. Oh, I'm a little bit off the screen. So each vertex of V shows up in the sequence how many times? Well, 4 shows up once. 3 shows up twice. And 1 shows up twice. Do you see the pattern? Do we see the pattern here? Look at the degree of 4. Well, let's expand a little bit. So none of the leaves show up. The leaves have vertex 1, or sorry, degree 1. 4 shows up once. It has degree 2. 3 and 1 show up twice. They have degree 3. So this isn't a coincidence. It turns out that each vertex V in the tree shows up in the sequence exactly the degree of V minus 1 times. Okay, so 1 and 3 have degree 3, so they show up twice in the sequence, and 4 is degree 2, it shows up once, and none of the leaves show up at all. And this is not a coincidence. This is something, if you trace through this process, of course, it's going to be clear why it has to work this way. Now, let's go in the other direction. So this is 2. So this is assigning a labeled tree to a sequence. Now, you may try to think from this picture, for instance, on how to work backwards, starting with this sequence, how to work backwards. But I'm going to give you the rundown here, and we're going to see if you think this process applied to that sequence works backwards in the way that you want it. Okay, so what are we given? We're given a sequence. We'll call the entire sequence sigma. The sequence will consist of characters A1, A2, A3, and so on, out to A sub k. And these are entries with each A sub I entries from the set. That is the set 1, 2, and so on, up to k plus 2. Okay, so first step. Draw k plus 2 vertices. Maybe I should switch to Roman numerals here, since this was a 2 and the other previous thing was a 1. So draw k plus 2 vertices, label them v sub 1 to v sub k plus 2. Let S be the set of indices. Before I even move on here, why does it have to be this way? Right? So why does it have to be this way? Someone asked in chat, how do I construct a proof or sequence from the last example? Well, that is what I did. So like this example, going through this step is constructing the proof or sequence. That's where this comes from. So okay. So now the thinking about if you're confused as to where this k plus 2 comes from or why this would be needed, well, consider our last example where in the proof or sequence we had 5 entries, but we know that the resulting, or rather the tree that this came from, was a tree on 7 vertices. So this is, when I look at the sequence, the length of the sequence is not the number of vertices in the labeled tree. It's actually the number of vertices in the labeled tree is the length of the sequence plus 2. So that's where this comes from. Of course, k plus 2 in this instance would be 7. Okay, in that example. Okay. So second step, let I be equal to 0. Let sigma sub 0 be the sequence that we started with, and initialize S sub 0 as the set of indices that we started with. Now you might consider, how are we adding back in the leaves at each step, right? So, I'm going from here. How do I go from here to here? I need to add in a leaf somehow. How do I do that in a way that makes sense? Well, let's let J be smallest number in S sub I that does not appear in the sequence, sigma sub I. Okay. Once I have identified that J, then I need to place an edge between the vertex V sub j and the vertex whose subscript appears first in the sequence sigma I. So place an edge between V sub j and the vertex whose subscript or index appears first in the sequence sigma sub I. Step 5. Remove the first number in the sequence. Sigma sub I to create the next sequence, sigma sub I plus 1. Remove the element j from the set S sub I to create S sub I plus 1. And 6. If this sequence is empty, place an edge between the two vertices whose subscripts are in S sub I plus 1 and stop. Otherwise, increment I by 1, return to step 3. So if the sequence is empty, I should say the sequence I'm referring to here is the sequence sigma sub I plus 1. So if the sequence sigma sub I plus 1 is empty, place an edge between the two vertices whose subscripts are in S sub I plus 1. And stop. Otherwise, increment I by 1 and return to step 3. Okay. Now, first, I want you to do something. So I'm not going to do it. I'm just going to flash it on the screen. So here's, I want you to check on your own. Starting with the sequence 43131, produce the tree T using this assignment. So here's the tree that you should end up with. Here is the sequence. Start with this sequence. Use this process of assigning the labeled tree to a sequence and see that what you end up with is the tree that you started with here. Okay, you will if you did it correctly. I suggest you draw these 7 vertices in that arrangement just to make it easier to see that these are in fact what you end up with is the same. And yeah, that's it. This basically is our proof of Cayley's tree formula, because this showing that both of these things, are rather showing that both of these things are not ambiguous, so you end up with the same thing. If you run this through the process and run it through the reverse process, you end up with the same thing. This is a proof that you have a bijection between those things, or one-to-one correspondence between those things, which says that they have the same count. Okay, they have the same count, and it's easy to count that set of sequences. So n to the n minus 2 is the number. Okay. So that's an example of where the proof, which is a combinatorial proof, essentially. The proof was very illuminating because the proof itself actually gave us a process for an algorithm for determining these things. So that's nice. That's an example of where the proof can illuminate something. The next proof is fine, but it is not exactly going to be that sort of illuminating, and so I'm mostly going to skip it. It's also rather long. It's like maybe it's like 2 pages long, so I will leave it to you to read, but the result is very important, and this is known as the Matrix Tree Theorem. What does the Matrix Tree Theorem say? So, if you could think of Cayley's theorem as basically giving you a count on the number of spanning trees of complete labeled graphs, the Matrix Tree Theorem applies to labeled graphs in general. So Cayley's theorem was about the trees, the spanning trees for a graph. Matrix Tree Theorem really so this applies to labeled graphs in general. This was proven in 1847. Again, my long spiel from yesterday about how if you're doing math that's only like 40 years old, that's like cutting edge stuff. Anyway, this is basically brings a relationship between spanning trees and matrices here. So before I state the theorem, I'm going to have to define some matrices that have pretty straightforward definitions that you might, me just telling you the name of them, you're probably going to be able to come up with what these matrices actually are. But yeah, so let me define if G is a graph of order n with vertices v1, v2, and so on out to v sub n. The degree matrix of G is the n by n matrix D whose ijth entry is the following. So remember, this is our notation for the ijth entry of a matrix. This is the degree of vertex v sub I if I is equal to j and 0 otherwise. So we use D not just because it's the degree matrix, but also this is a diagonal matrix. This is the matrix that contains the degrees of all the vertices on the diagonal and 0 everywhere else. Right? And so we have, what does D look like? It's so the degree of V1, degree of V2, so on down to degree of V sub n, and it's 0 everywhere else. Okay. Recall from linear algebra. The ijth cofactor of a matrix M is defined to be the following. So given n by n matrix M. This is a matrix, not a special kind of matrix, not a degree matrix, adjacency matrix, any of that. It's just any matrix that is a square matrix. Okay, we can talk about the ijth cofactor of that, the ijth cofactor of M is defined to be -1 to the I plus j. Sometimes you'll see this written as like C sub ij, whatever. Like you can write it like that if you want to. But this is -1 to the I plus j times the determinant of the matrix M. I'm going to write it as just, well, I'm going to follow the textbook here, even though this notation is kind of annoying. M I vertical bar j, okay, where, of course, det is determinant, but you already know what this M notation is, where this is the n minus 1 by n minus 1 matrix formed from M by deleting the ith row and jth column. Okay. All right, so this is linear algebra stuff. Degree matrix is a new thing that we define, but we need all of this to be able to state this theorem. So this was due to Kirchhoff. So I'm not going to give the proof, but I will tell you where you can read it. But let me state this thing. So what is the matrix tree theorem? So this is the statement. If G is a connected labeled graph with adjacency matrix A and degree matrix D, then the number of unique spanning trees of G is equal to the value of any cofactor of the matrix D minus A. So the proof of this is on pages 48 to 50. Let's actually have a look at the following. So I'm going to do an example here. Actually, you know, let's make it easy here. So I'm gonna, can I fit it on this page? I'm going to put it on another page, but I'm going to bring this page back. So let's see an example of this. So I'm going to look at a labeled graph G on 4 vertices labeled V1, V2, V3, V4. The graph that I'm going to do this for is this one. So let's look at, by the Matrix Tree Theorem, the number of unique spanning trees is equal to the value of any cofactor of the matrix D minus A. So let's come up with D and A first. So number of unique spanning trees G is equal to any cofactor of D minus A. Well, what is D here? D is the 4x4 degree matrix that we have. What is the degree of V1 here? 2. What is the degree of V2? Also 2. What is the degree of V3? 3. What is the degree of V4? Also 3. So there's the degree matrix of G. The adjacency matrix of G is what? So the adjacency matrix, I have 0. V1 is not adjacent to V2, so 0. V1 is adjacent to V3 and V4, so 1, 1. In the second row, V2 is only adjacent to V3 and V4 as well, so this is 0, 0, 1, 1. V3 is adjacent to V1, V2, and V4. So this is 1, 1, 0, 1. And V4 is adjacent to V1, V2, and V3. So this is 1, 1, 1, 0. So there's our adjacency matrix. Here is our degree matrix. The matrix D minus A is what? Well, let's just do it. So this is the 4x4 matrix. We have 2 minus 0, okay, and then 0 minus 0, 0. 0 minus 1 is minus 1. 0 minus 1 is minus 1. Okay. The next row, 0, 2, minus 1, minus 1. Okay, we have 0 minus 1, 0 minus 1, 3 minus 0, 0 minus 1, 0 minus 1, 0 minus 1, 0 minus 1, 3 minus 0. There it is. We were told that we can pick any cofactor we like, right? So let's just, what do we want to do here? Let's see. So let's pick one that has some zeros in it. So let's do the 4, 4 cofactor, right? What's the 4, 4 cofactor? This would be minus 1 to the 4 plus 4. That's minus 1 to an even power, so that goes away. I don't have a minus 1 here, and this is the determinant of the 3 by 3 matrix I get deleting the 4th row and fourth column. So it's the determinant of 2, 0, minus 1, 0, 2, minus 1, minus 1, minus 1, 3. It's a 3 by 3 determinant. You can do it however you want to. But here, I'm just going to expand across the first row. So this would be 2 times the determinant of 2 minus 1 minus 1, 3. Minus 0 times stuff I don't care about, plus minus 1 times the determinant 0, 2, minus 1, minus 1. So this is 2 times, this would be 6 minus minus 1. So this would be 6 minus plus 1, so this would be 2 times 5. Okay, minus 0 plus minus 1 times 0 minus minus 2, so that's plus 2. So this would be 10 minus 2, which is 8. So what I'm claiming is that 8 is the number of unique spanning trees of G. So this is equal to 8 according to this computation. Is that true? Are there 8 unique spanning trees for that graph? And the answer is yes. And here they are. So there's all 8 of them. But you see that we didn't need to come up with all of these to compute the number if this theorem is true. And it is. Okay. So this is another powerful tool. Both of these results are very, very nice. And immediately answer some of these enumeration questions you might have, because immediately when you're talking about all these properties of trees and spanning trees, it's a question of how many such things exist. When you have real world applications and problems that would be nicely handled if you could compute a spanning tree or minimum weight spanning tree or any sort of need to find spanning tree for a graph, this is a blessing that you have the ability to enumerate them like this. And this is just kind of the first taste of this big overlap between combinatorics and graph theory. So, of course, in the later parts of the course, we're going to be focused almost entirely on enumeration, but this is just one aspect of this. Okay. So, a quick aside about the Koenigsberg bridge problem. So, quickly. A return to the Koenigsberg bridge problem. So recall, you had a landmass, we'll call it C, you had a landmass A, you had another landmass B, and you had a landmass D. And there was a bridge between A and D like this, bridges connecting D to both B and C, and then bridges like this. Maybe to make it clear here that these are bridges, I'll do this. Okay. Now, you could say, what was the problem, right? The problem was traversing each bridge exactly once. After some attempts to do this and failure, you might convince yourself very quickly that it's not possible. But actually setting about to prove why it's not possible takes a sort of thinking that, especially when this is encountered by Euler and other mathematicians, uh, they were a little bit puzzled because, most of the explosion in mathematical development happening post like Renaissance was in the direction of math that would mostly be called like algebra and analysis, especially analysis, which involves computing, right? Like when mathematicians of this era talked about calculating and computing, a lot of the computations was a lot of algebra, and it was also it was computations involving like derivatives, right? Was the big thing. So once you have the ability to take derivatives and integrals, and deal with differential equations and try to solve differential equations, that was the sort of computing and calculating that they were most focused on. That was where almost all of the mathematical development was happening. But then around like the periphery of math, there started to arise some questions that that sort of computation wasn't super helpful for, or at least didn't really have the same tools. Some of this was due to the fact that the mathematicians were kind of playing fast and loose with some of the underlying logic, so they were doing things that didn't really make sense, like early, how mathematicians dealt with infinitesimal quantities. Early was a little bit hand wavy because infinitesimals don't exist, but they treated them like they existed, so there was a little bit of ambiguity there, and that sort of stuff wasn't really smoothed out until like the mid 1800s. Karl Weierstrass was like the big guy that if you've ever seen an epsilon delta proof in your life, he is to blame for that. So you needed that sort of thing. See, epsilon delta proofs and analysis for dealing, with definitions of continuity and stuff, that sort of thing didn't exist till the mid 1800s. So consider all of the math that was done prior to that, involving differential equations and lots of pretty high-powered things. Plenty of partial differential equations. A lot of work was done on some very advanced stuff before they even had like a rigorous, precise definition of limit, right? So that's something to keep in mind. A lot of it was because of that, but sincerely, a lot of the other stuff was just because it was a problem that hadn't really been considered for that angle. So topology is like this. Topology arises from these sort of things, and so does these questions of like graph theory. And then even later and around the same time, geometry was also kind of undergoing a crisis of trying to understand what was actually important or not. A question in the chat: if two graphs have the same number of spanning trees, does that mean they're isomorphic? Oh, you should think about that one. I want you to think about that one. Do it for small vertices, small number of vertices. See if you can come up with two graphs that are non-isomorphic that have the same number of spanning trees. See if you can do that. Okay, but what was it? How did Euler think about this? So I'm going to read off Euler's solution. Okay, so Euler's solution is this. Basically, you use a figure like this. You can use the sequences of letters like this to describe routes. And the idea was that you would use this to describe a route where no bridge was repeated. So the only valid routes were those where no bridge was repeated. And so, for instance, maybe you say like A, B, D, A, C, AB is a route. What would this route mean? So I would start at A, I would cross to B with one of these bridges. Okay, so one of them gets used to cross to B. From there, I cross to D in the only way that I can. So we'll say that bridge. So here in this first one, let's say that I use this bridge. Okay, so I crossed from A to B using this bridge, from B to D using the only bridge I can, to A using the only bridge I can, to C using one of these bridges. We'll say I use this one. So I cross to C. Back to A using the bridge I didn't use when I crossed to C. So now I'm using this bridge. Back to B, again using the bridge that I didn't use the first time. Here, back to B. I did not traverse a bridge more than once, but I missed this bridge. So I missed this one. Right? So this is a route. Call it a route. Here, as I'm saying, a route is something that doesn't use the same bridge twice, is a route that misses the C to D bridge. Okay. And so these bridges you could identify with different labelings, right? You could say this is a bridge A to B or B to A, and I mean maybe that's even the way that you label this, right? Where you call this bridge the A to B bridge and this bridge the B to A bridge, so on, to distinguish them. You could use pairs of letters to denote bridges in this way. And so here is, in Euler's own words, this is what he wrote. The problem is therefore reduced to finding a sequence of 8 letters formed from the 4 letters A, B, C, and D, in which various pairs of letters occur the required number of times. Before I turn to the problem of finding such a sequence, it would be useful to find out whether or not it is even possible to arrange the letters in this way, for if it were possible to show that there is no such arrangement, then any work directed toward finding it would be wasted. I've therefore tried to find a rule which will be useful in this case and in others for determining whether or not such an arrangement can exist. And so here was the argument. So Euler argued that since land area D is connected to 3 bridges, then D must appear in the sequence 2 times. Because if it only appeared once, that wouldn't get you all of the bridges. If it appeared more than twice, it would represent multiple crossings of at least one bridge. So D has to appear exactly 2 times. What did Euler say? So D appears twice in a perfect route. Okay. All right. Well, what about B and C? B and C also have to appear twice. For the same reason. More than twice, you'd be crossing a bridge multiple times. Less than twice, you'd be missing a bridge. Just like in this case, this route, since D only appears once, we actually missed this one bridge that crossed at D, or crossed with going to D. What about A? We will see. I might have you do this in homework 3. A must appear 3 times. For the same reason that if it appeared less than 3 times, you would miss a bridge. If it appeared more than 3 times, you would cross a bridge multiple times. Remember, in the sequence, passing to the letter and away from it represents crossing 2 bridges, right? But a perfect route has what length? A perfect route has length 8. perfect route is going to consist of 8 characters made up of A, B, C, or D. But D has to appear twice. B and C also each appear twice, so that's 6 slots. And A must appear 3 times. So you would have, there has to be a 9-letter sequence that has to fit in 8-letter slots, so it's impossible. And this was his rationale for the Koenigsberg bridge problem being impossible. He discussed other problems of the sort. You can change the land masses up ever so slightly. I'm going to read you a little excerpt that basically was his appeal to. This is like his appeal to this truly being a different type of math than had been considered at the time. And as I said, whether you're a graph theorist or topologist, most will say that this is, you could either consider it the birth of graph theory. It's definitely that. It's also, in a way, the birth of topology, because some of these things being discussed had never really been talked about before. So in addition to that branch of geometry which is concerned with magnitudes and which has always received the greatest attention, there is another branch previously almost unknown which Leibniz first mentioned, calling it the geometry of position. This branch is concerned only with the determination of position and its properties. It does not involve measurements nor calculations made with them. It has not yet been satisfactorily determined what kind of problems are relevant to this geometry of position, or what methods would be used in solving them. Hence, when a problem was recently mentioned, the Koenigsberg problem, which seemed geometrical but was so constructed that it did not require the measurement of distances, nor did calculation help at all. What he's saying when he says calculation didn't help at all, he's saying that, like, taking derivatives, right, didn't help. Like, there was no function to take a derivative of, or to talk about its derivatives or its integrals or anything like that. That's what he means when he says that calculation didn't help at all. So, nor did calculation help at all. I had no doubt that it was concerned with the geometry of position, especially as its solution involved only position and no calculation was of any use. I have therefore decided to give here the method which I have found for solving this kind of problem as an example of the geometry of position. So you can see that what he is calling the geometry of position, you could either interpret as graph theory or topology, or some mixture of the two. So that is that. We're actually going to return to this. As I said, here's a nice here's a nice other example of a Koenigsberg bridge problem, where you have more land masses and more bridges. See if you can cook up a sequence that works for those of a perfect route. This leads naturally, though, to, and we'll recast some of this a little bit later, this leads us kind of intuitively to the following properties that a graph might have. So, using this kind of analogy with the Koenigsberg bridge problem, this idea of a perfect route in a graph leads us to the idea of Eulerian trails and circuits. In a graph G. Okay. So recall, been brushing up on this because of the homeworks and stuff, but recall when we were first going over all this terminology, what is a trail? A trail is a graph, or a trail in a graph is a walk that does not repeat any edges, right? A trail in G is a walk that repeats no edges. Repeating no bridge traversing, right? So this repeats no edges, and that a closed trail, one that begins and ends at the same vertex, is called a circuit. Okay. If a trail in a graph G includes every edge of G, then that trail is said to be an Eulerian trail. So traversing every bridge, right? And it repeats no edges. So traversing every bridge exactly once. Okay. Similarly, an Eulerian circuit in a graph is a circuit that includes every edge of a graph. So an Eulerian circuit in a graph is a circuit that includes every edge of G. A graph that contains an Eulerian circuit is said to be an Eulerian graph. Is said to be an Eulerian graph. Can you see the analogy here with our, quote, perfect root from the Koenigsberg bridge problem corresponding to an Eulerian circuit of a graph? Okay. So, what are some examples of these Eulerian graphs? You can think of one off the top of your head, I think. Maybe a few off the top of your head. What are some examples of Eulerian graphs? So there's cycles, all right? They have the obvious Eulerian circuit just going in the cycle, right? The paths have no circuits, so they're not Eulerian because there's not even you can't even have a circuit in a path. Let's do a couple more. Let me give a couple of questions here. I can fit it here at the bottom. The question is this graph Eulerian? Well, let's try to identify an Eulerian circuit, right? There's not that many vertices. Going, well, that here is an Eulerian trail from this vertex to this vertex. So let's, that's an Eulerian trail from here to here. I repeated no edges. But that's not an Eulerian circuit, so Eulerian circuit, I need to pick some vertex and see if there's a way to get there without repeating an edge. So let's repeat, or let's try this vertex. All right. So for this vertex, here, 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 here. That's a circuit, but it's not Eulerian because it doesn't traverse every edge of the graph. So I missed this one. If I'd started here and went here, 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 and here, now I have to repeat edges. So that wouldn't be a circuit. Okay, so starting at this vertex, it seems like it's going to give us problems. For the same reason, it looks like starting here is going to give us problems. Can we have how about an Eulerian circuit if I start here? So I've missed that. What did I do? I've missed. Oh, well, What about this vertex? Mm, 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 mm. I'd have to repeat an edge. This isn't looking hopeful, right? So see if you can put into an argument as to why this is not Eulerian, what it is that's going wrong here, or if you can figure out what is happening here. Or can you find, did we miss something? Was there an Eulerian circuit that I just missed there? How about the next one? Let me give another example. Is this Eulerian? Well, I'm going to start here and just see if at this vertex I can find a Eulerian circuit here. So, uh, mm, 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 that doesn't hit all the edges. Well, maybe I just screwed up there, right? Let's start here again. I can go here, 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 here. Uh, uh, oh. Let's see. Did I actually manage to do it? So I've missed this edge so far. That does it, right? So I hit every edge there, made it back to this vertex, hit every edge only once. So the answer is yes. See if you can find other Eulerian circuits. Is that the only one? We're only required to have one Eulerian circuit. If a graph contains a single Eulerian circuit, then that's it. That does it. But the question is, what sort of restrictions does being Eulerian place on a graph? So question. What sort of restrictions does being Eulerian place on a graph G? This may not be immediately clear why this is. I'm not going to have time, I don't think, to prove it today, although what I might do is talk about kind of a corollary here and just very briefly discuss the proof. Maybe I'll discuss the proof at the beginning of the lecture tomorrow, so I'll just go ahead and state the theorem. So here is the answer to this. Theorem. For a connected graph G, the following statements are equivalent. One, G is Eulerian. This is equivalent to 2, every vertex of G has even degree. And 3, the edges of G can be partitioned into edge disjoint cycles. Now, I claim that this is Eulerian, so let's at least verify that for this example these things are true. Does every vertex in this graph have even degree? Degree of this is 2. Degree of this is 1, 2, 3, 4. Degree is 4, degree is 4, degree is 4, degree is 2. All of the vertices have even degree. Obviously, having degree 1 is a problem for having an Eulerian circuit. So having, like, say, a leaf in a tree, right? But just being degree 1, period. Having degree 1 is a problem because if you get to that vertex, you can't go back, right? And if you start at that vertex, you can't go back to it without repeating that edge. So degree 1 is clearly a problem. But why is odd degree a problem? Well, think about that a little bit. Like I said, I'll discuss the technique of the proof for next lecture. But yes, we verified that all these vertices, in fact, have even degree. What about this example? This has degree 2, degree 2, degree 2. This has degree 1, 2, 3, 1, 2, 3. So, no. You have vertices of odd degree, so it does not satisfy this. Okay. All right. So this satisfies every vertex has even degree. This third condition might be a little bit confusing when you read it. You might be wondering what it is that's actually being said here. So what is it that is being said when I say the edges of G can be partitioned into edge disjoint cycles? Well, look at the trail that the circuit that I came up with here. I specifically actually made use of this partitioning. How? What partitioning am I talking about? The edges in this graph can be thought of as 2 edge disjoint cycles. So they share some vertices, but they don't share any edges. The 2 cycles in question, I really need to get a different colored pen to illustrate this, but the cycles in question are these. There's one of them. That's cycle 1. Cycle 2 is that one. Okay. So cycle 1 is this like figure 8 sort of thing. And cycle 2 is around this square. Notice none of those edges belong to the other cycle. So that's what I mean when I say that they're edge disjoint. Okay, so I get 2 cycles I didn't claim that it can be partitioned into just two cycles or an even number of cycles or whatever, but you have to be able, or you have to be able to partition it into an edge disjoint cycle. The graph G may be a single cycle, right? So cycles are examples of Eulerian graphs. So if it can be partitioned into a single cycle, that still counts. But otherwise, it can be partitioned in this manner, where the edges of the graph form some number of edge disjoint cycles. Okay. So that is the idea. And so Eulerian circuits exist in connected graphs precisely when the degrees of every vertex are all even, right? So all the degrees are even. But what about Eulerian trails? What if we don't require it to be a circuit? What if we're just talking about Eulerian trails now? So if an Eulerian circuit exists, of course, that is an Eulerian trail. It's just a closed one. The question is, are there graphs which are not Eulerian, but which do contain an Eulerian trail? Well, it turns out this theorem can apply to answer this question, and there is the following corollary of this theorem, which says that the connected graph G contains an Eulerian trail if and only if there are at most two vertices of odd degree. This is the only thing that's allowed. But hey, we know that we have an example having two vertices of odd degree where we found an Eulerian trail. We just didn't find an Eulerian circuit. It's this one, right? The house. So this one has an Eulerian trail, which we found before. It just didn't have an Eulerian circuit. So here, there, that's an Eulerian trail from this vertex to that vertex, right? It traverses every edge. It never repeats an edge. It's not an Eulerian graph because that is not an Eulerian circuit, and it's impossible to find an Eulerian circuit. But it contains an Eulerian trail. So is this Eulerian? No, but it contains an Eulerian trail. It's not the only one it contains. You could start at this endpoint as well. See if you can find any others. So it contains an Eulerian trail, which does mean it's a little special, but it's not Eulerian. So these two vertices have degree 3. Those are the only two vertices with odd degree. The rest of the vertices have even degree. So you satisfy the requirements of this corollary. Okay. And you can think yourself about how this is a corollary of this theorem. You will prove this corollary in homework 3, okay, which, of course, don't have to worry about homework 3. You haven't even started on homework 2, probably, so it's fine. But homework 3 will be assigned at the end of this week. It'll be assigned on Friday. Anyway, that is that. That is all I have time for today, I think. So, so I'm going to stop here. Next time, we're going to talk about an algorithm for identifying Eulerian circuits. Which is useful, of course, if you're trying to think of, what's an efficient manner of actually finding an Eulerian circuit without needlessly confusing yourself. So we'll talk a little bit about that. We'll move on to Hamiltonian paths and cycles, and then we're going to move on to some what are called forbidden subgraph results, which I built up a little bit in last week's lectures near the end of the week. So anyway, that is the immediate plan. As always, let me know if you have any questions about any of this stuff, whether it's pertaining to homework or not, or just general questions about the material or schedule or any of that stuff. Just let me know. So anyway, I will see you all tomorrow, same time.